Okay, kiddos, let's take a look at solutions to our practice tests for work, energy, and momentum. First question says, Mr. T lifts a 3 kilogram textbook from the floor to the top of the table, which is 1.2 meters tall, so it's above the ground. Assume he lifts the book at a slow, constant speed. So what this means, assume he lifts the book at a slow, constant speed. If he were to lift it very quickly, the book would accelerate upwards. And in order for it to accelerate upwards, I'll make a little free body diagram here. In order for it to accelerate upwards, the force in the upward direction would have to be more than the force in the downward direction. So figuring out the force that he exerted would be more challenging. But because it's at a slow, constant speed, we know that the force in the upward direction is the same as the force in the downward direction. So the force he exerts in the upward direction will just be the book's weight, not mass. Whoops, not mass, but weight. So first question clues us into that. What is the weight of the book? And weight is equal to mg. So who knows what happened here? Oh, who knows what happened here? But we have mass times acceleration due to gravity, 29.4 newtons. So that is going to be the force that he has to exert. So 29.4 newtons downward, 29.4 newtons upward. 3, how much work does he do? So this is work is force times distance, and the force he exerts is the weight of the book. The distance he moves the book through is 1.2 meters, and we multiply and get something in joules. So this is the amount of energy he has to expend in moving the book from here to here. If you were to hook up a motor to it and plug the motor into the wall, it would, well, if it were 100% efficient, it would use 35.28 joules to move the book up like that. Notice how the direction of the force he exerts and the direction in which it goes are the same. That's why we just multiply. 4, how much potential energy does the book gain? So here's what I say. The work done on the book went into increasing the potential energy. And we know that because there was no friction involved, so energy wasn't lost due to heat, and the book did not speed up, meaning energy was not, or the work was not turned into kinetic energy. So all the work done went into the potential energy. And I give some specific information here. Work done will equal the potential energy gained for an object lifted slowly. So no acceleration, and it's being lifted up. This would be different for an object being pushed to the side. So once we know this, we've already calculated it. But over here, I show, well, suppose that concept were a little fuzzy to you and you weren't really sure. You could just plug into the formula for potential energy, mgh, and the mass and acceleration due to gravity and the height of the book at the top of the table. This is this. 2 ways to solve that. Notice how the numbers multiplied are exactly the same. 3, 9.8, 1.2, and we did 3, 9.8, and then 1.2. Aha! 5. If the book were to fall from the table, how fast would it be going just before it hits the ground? So for this situation, potential energy lost equals kinetic energy gained. So something that is falling, assuming no air resistance, this is a situation. Potential energy lost equals kinetic energy gained. So we know if it has 35.28 joules of potential up here and it falls right before it hits the ground, it will have a kinetic energy of 35.28 joules. So simply setting that equal to the formula for kinetic energy, 1/2 mv squared, we solve, and I think this is what I ended up with using the calculator. Why don't you check that out? 4.85 meters per second. So if you wanted to really go in depth and check your work, you could use the kinematics formulas, and it would be like this, using final velocity squared equals initial velocity squared plus 2AD. And so you would plug in 0, you would solve for final velocity to 9.8 and 1.2. And you should end up with this. Where are we? Here we are. Okay, next question. So Lance, I think maybe I wrote this before Lance Armstrong was a scandal. Lance and his bike have a mass of 80 kilograms. He starts from rest on a 1 mile long hill that makes an angle of 20 degrees. That's actually really steep for a bicycle with respect to the horizontal. And then some additional information. You don't have to have this memorized, but there are 1609 meters in 1 mile. So here's our diagram. Lance is up here. That's a bicycle. And the hill looks like that. So we can make a right triangle. And the reality is that the hill could go like this. Oh, I can't undo that because I'm recording. Never mind. The hill could go like this, or the hill could be like this. And because we're assuming no friction, he's going to be going the exact same speed down here in all of those different situations. Because we say the potential energy at the top will equal the kinetic energy at the bottom. So as long as no energy is lost due to friction, potential energy at the top will equal kinetic energy at the bottom, because he's starting at rest, so there's 0 kinetic up at the top, and 0 potential at the bottom, because this is ground level. So the thing we're really interested in is the height. So using SOHCAHTOA skills, we can figure out that the height of this hill above ground is 550.3 meters. So potential energy at the top of the hill, mass times g times the height of the hill, and that's a whole lot of joules. I expressed it in kilojoules as well, just for fun. And let's see, assuming no friction, what would be his kinetic energy at the bottom of the hill? So, assuming no friction, we know that the potential energy up at the top will equal the kinetic energy at the bottom. So we have this big number of joules equals 1/2 mv squared. And I think, why don't you plug this in? I was kind of approximating, but looks like velocity is 103.9 meters per second. And then a little, let's get in touch with reality here. Riding a bike for an entire mile and experiencing 0 friction is totally unrealistic. So if you have the experience of riding a bike that, riding on flat ground at 20 miles per hour is actually really difficult. And you'll notice the wind resistance, the air resistance is very strong. So, to accelerate for an entire mile is totally unrealistic. This speed is actually over 200 miles per hour. So to think of a bicyclist coasting down a hill going 200 miles per hour, even if they were to jump out of a plane with a bicycle, they wouldn't go 200 miles per hour because of air resistance. But neglecting friction, this is how fast he would be going. So I'm going to pause here and then create a different video for the next pages because I have this 15-minute time limit.